Sixth problem, 610. Here we have rather unphysical two massless pulleys. This is a pulley which is massless, and here there is a pulley which is massless. And there is a string over the pulley. The string is also massless, goes under here and goes through there. So this is a string. The string is massless. The pulleys are massless. It's attached here. The pulley is hanging here. And there is also no friction anywhere here. So it's a little bit artificial. This has a weight, a mass hanging capital N, and on this pulley is hanging a weight little m. The angle here is theta, and the angle here happens to be the same, is also theta. We are being told that there is equilibrium. In other words, that m is not going down, capital M, nor going up. Well, that is only the case if the sum of all forces is 0. I will decompose in y and x direction. It's often very handy. So it means that the sum of all forces in x direction must be 0, and independently the sum of all forces in the y direction must be 0. Let's make free body diagrams. Here it's easy. We have mg, and here we have tension T. The two must be equal, otherwise there would be acceleration. If the tension is T here, then the tension must be the same everywhere in the rope, because the rope is massless. Imagine that I had a little section of rope here, and that the tension here would be different from the tension here. Then this massless rope would get an acceleration which is infinitely large. 0 mass, the two tensions would be different, get infinitely high acceleration, so that is clearly not allowed, that's non-physical. So therefore, whenever you deal with a massless string and no friction here and no friction there, the tension along the string is everywhere the same. And so I can also put the tension here, because that is important for the force acting on this pulley. Of course, I could have put the tension here down, and I could have put the tension here down, but we're not dealing with that here, so I've left them out. And then here I have mg. So on this object there are three forces. These two tensions plus little mg. On this object, capital the tension plus capital mg. Now the sum of the forces in x directions are immediately 0. I don't have to demonstrate that to you, because these are the two horizontal components of T. It's clear that they immediately cancel each other out. But now in the y direction. In the y direction, T must be equal mg if we have equilibrium. So that's 1. And for this one, the vertical component of these two tensions must exactly cancel out mg. Now if this angle is theta, then this is also theta. So this vertical component is T sine theta, but I have two of them. So what do I get? I get 2T times the sine of theta equals little mg. And that is my second equation. Now suppose theta and little m are known, then I can find capital M, because I can eliminate T from these two equations. And you will find then, which is rather trivial, that capital M is little m divided by 2 times the sine of theta. So for a given value of little m and for a given value of theta, you immediately find what capital M is. And if you were interested in the tension, well, you can either use equation 1 or you can use equation 2, and you will even be able to solve for the tension. Now we're going to pull M down. We're going to pull this one down, and we want to know what's going to happen. Well, I'll already tell you what's going to happen. The system is going to oscillate, but I want to be a little bit more quantitative about that. if I pull one down, then I pull down with a force which I call force Walter Lewin. And the only way that it can still be equilibrium is that the tension on capital M must go up while I'm holding it in my hand. So here is that object capital M. I have here mg. I have here the force by Walter Lewin. And this T, which I will call T prime now, not to confuse it with the previous one, must exactly balance out these two forces. And so I would now get, to have equilibrium, I would get T prime equals the force by Walter Lewin plus mg. For the other object, for little m, I would get that T2 prime, because the tension is the same everywhere, times the sign of theta prime, theta has changed, equals mg. So this is equation number 3, and this is equation number 4. And as I pull capital M down, it should be obvious that little m goes up. I can't find my drawing anymore, but oh my goodness, I can't find my drawing anymore. It must have somehow disappeared. Oh, it's flipped off all the way. Well, it's all the way there on the floor, so we'll just leave it on the floor. But it's immediately clear that if I pull this one down, that little m will go up and that the angle thetas will become smaller. Now, let us assume that I let go all of a sudden. So this force all of a sudden becomes 0, but the angle theta prime is not changing instantaneously. So immediately T prime goes down. So this T prime goes down. And as this T prime goes down, notice that there is no longer equilibrium here. You now have a net force here, which is not 0. The net force on this little m, on this little object m, is now in the, if I pull this down, and this object went up, the net force is in the down direction. mg minus 2t, I'll call it now double prime, which is now the tension immediately after Walter Lewin lets go, times the sine of theta prime equals m times the acceleration in the y direction. This is no longer 0. Remember, this was 0 here when there was equilibrium. But when T prime goes down and theta prime remains constant, this becomes a positive value, and so the object is being accelerated downwards. And of course, it's immediately obvious that if I had pushed little m down, then capital M would have gone up, that the whole system would have started to oscillate in this direction, and so you get an oscillatory situation. It may be a challenge for you at any moment in time for a given value for theta to calculate what the tension T is. I call it here T double prime as a function of the acceleration in the y direction. I will not do that now, but I mentioned to you that T prime goes down at the moment that I let go. Don't think that T prime becomes the same value as T as we had before when Walter Lewin was not touching them. No, T prime will indeed go down to T double prime, but will not become as small as T. It will be a little larger. And you can see that it has to be a little larger, because otherwise this object would not accelerate upwards. And if I pull it down and I let it go, it's being accelerated upwards. Give that some thought, and if you have some time, work out the equations while the motion is underway.